All right, guys. Everybody have a note sheet. Everybody's got a note sheet. Yes.
Yes. Ray does too. He's a liar. Not a liar. He just likes to be different. I don't actually have it.
Questions on the homework before we get started? Questions?
It was probably easy.
I already know how to do this. What if you don't?
So what we're looking at today is adding and subtracting rational expressions. Now we're going to start off with like denominators, because if the bottoms of the fractions, the denominators are the same, we can add or subtract the numerators. We don't have to do anything with it. Because they give us this example here, we could say it's like 1/4 plus 3/4. Because if the denominators are the same, we add the numerators. Yes, because 1 plus 3 is 4. 4 over 4 would be 1. It's nice, it works, we can add and subtract. But the denominators have to be the same. And again, they throw this in here with C different from 0. All that means is that the denominator cannot be 0. We can't divide by 0. All right, guys, let's focus in here.
So is it going to be 4x or 10 over 4x?
So we have 7 over 4x plus 3 over 4x. So since the denominators are the same, we can add the numerator, 7 plus 3 over 4x. Well, 7 plus 3 is 10 over 4x.
I'm guessing you got to get x.
Well, it's not so much with the x, but if we look at this here, 10 over 4x, is there anything in common on top and bottom? 2. There's a common factor 2, yes? So we can reduce it, yes. So the 10 reduces to 5, 4x reduces to 2. And since there's nothing else in common on top and bottom, that's it. Questions on this here? All right, guys, let's stay focused. Now, we're not going to focus too much on it, but there are restrictions. Now, the restrictions are just the values of x that would cause the denominator to be 0. Because any values of x, in this case, or x and y, that would cause the bottom of this fraction to be 0 is going to be a restriction. And we look at what we started with, not so much the values that we have at the end. But here it really doesn't matter, because 4x and 2x will give us the same restriction. All right, guys. So here we're saying that if 4x is equal to 0, we have a division of 0, it doesn't work. So if x is, well, 0, the denominator would be 0. We can't have that. So we're saying that x cannot be 0. Because if x is 0, we have a division of 0, it doesn't work. All right, guys, focus in, focus in. Questions on the first one? Let's look at the second.
The numerators aren't the same, the denominators are. There's an x.
So let's see here. So the first main thing to add or subtract is, are the denominators the same?
Yeah.
So since the denominators are the same, we can subtract the numerators. So we're going to have on top 2x minus 5 over x plus 6. 2x and 5, are they like terms? No. So is there anything we can do with the top besides just saying 2x minus 5? No. Okay. Is there any way we could factor 2x minus 5? No, there's no greatest common factor. The degree is 1. The biggest variable attached to, or the biggest exponent attached to the variable is 1. 2x minus 5 is as simplified as it gets. Is there anything in common on top and bottom? Because it's very tempting to want to say this x and x and cross it out. Unfortunately, because of the plus, x plus 6 on the bottom, it is stuck together as one term. If it was x times 6 or 6x, and 2x times 5, where we had this multiplication, then we can simplify. We can simplify with our multiplication. But whenever we have this addition or subtraction between the terms, it locks them together. Because the only way we could simplify, quote unquote simplify this, is by splitting the numerator back apart. But that would take us back to where we started. That's not simplifying, that's going backwards. So this is as simplified as it gets. This is our final answer. Now, I'm not, again, as I've said before, especially with these here, I'm not going to really ask for the restrictions on the homework or the assignments. But our restrictions are going to be whatever is going to make the denominator be 0. In this case, x plus 6. And we can set it equal to 0. All right, guys. We can subtract 6 from both sides, telling us x cannot be negative 6. Because if x is negative 6, we have a division of 0. Does not work. Questions on addition or subtraction so far? All right. Let's look at the next one. 8 over 12x minus 5 over 12x. Now again, the denominators are the same. So we can subtract the numerators. Well, 8 minus 5 is over 12x. As long as there's not something in common on top and bottom, we are done. Is there something in common between 3 and 12x? 3, yes? So we do have something in common, yes?
1/4 x.
1 over 4x, yes. Since the numerator reduced completely, it reduces to 1, and we have to list it for the numerator. If the denominator reduced to 1, reduced completely, we don't have to write it. Division of 1 is understood, but 1 on top we have to list. All right, guys. 2 over 3x squared plus 1 over 3x squared. Since the denominators are the same, all we have to do to add these is add the numerators. Denominator stays the same, we add the numerators. 2 plus 1.
3.
Over 3x squared. Here on top and bottom we have a greatest common factor of 3. So the numerator would reduce to, and the denominator would reduce to x squared. So 1 over x squared.
What? Speaking.
All right, guys. Focus in, focus in. Questions on this here? Let's look at number 3. 4x over x minus 2 minus x over x minus 2. Now here the denominators are the same. So we just have x minus 2. And we can subtract the numerators.
Does it just turn into 4?
Not quite.
Nothing.
So 4x and x are like terms, yes? So 4x minus x, we have 4 of them and we take 1 away. We're left with
Shut up, Brady.
3x. Now 3x and our x minus 2 don't have anything in common. Again, it's very tempting to want to cross the x's out. But on bottom, that x minus 2, x and 2 are stuck together, they're a single term, so we can't just cross them out. And if we looked at the restrictions for this here, x could not be 2, because our 2 minus 2 would give us 0, so 2 is a restriction. Questions on this here? Because these are kind of nice, especially when the denominators are the same, because then we're just mainly focused on the numerators. Because on number 4, the denominators are both the same, x squared plus 1. So that means we can add our numerators together, our 2x squared and 2. Well, they're not like terms, so it just gives us 2x squared plus 2. Now here we do, there is indeed a greatest common factor in the numerator, right, which is
The whole numerator is 2.
2.
And then on top of
So in the whole numerator, we do have a common factor of 2. Now we're going to factor it out just to make sure nothing reduces on top and bottom. So if I factor the 2 out of 2x squared, we're left with x squared. Plus, if I factor a 2 out of 2, we're left with 1. So after factoring that 2 out, is there something in common on top and bottom? Is it
squared plus 4.
the x squared plus 1? Since we do have multiplication between our terms this time, they do reduce. Because our x squared plus 1 over x squared plus 1 reduces, leaving us with 2.
First time we had a single digit.
Now this one here, I do want to look at the restrictions. Because the restrictions for this one here are a little bit interesting. Because again, we said what's on the bottom of the fraction, in this case here, x squared plus 1, cannot be 0. So to do this, we'll set it equal to 0 and solve for the value of x, or x's. That would make this be 0. Now the first thing we can do to solve this here is subtract 1 from both sides. All right, guys. Telling us x squared is equal to negative 1. At this point here, we can take the square root of both sides. Our square root of x squared is going to be x. And whenever we take the square root of both sides, we have to put our plus or minus. Now, the square root of negative 1 is I. It's our imaginary term. Because we needed that for our quadratics to be able to find some of our solutions, because some of them were non-real solutions. But that also tells us something about this here, is that there's no real value of x that's going to make our x squared plus 1 be 0. And graphically, we can look at this here, x squared plus 1. We can graph it, and we see here that there's no value or no spot on this graph where it crosses the x-axis. So that means there's no value of x that will make this be 0. So for our restrictions for this here, there are none. Because for most of the time, we will have restrictions. We'll have values of x that would make the denominator be 0. Sometimes we won't. Doesn't always have to be. Questions on this here? I think we feel good with these here. These are the ones we like, especially when the denominators are 0. Or not 0, but are the same. But they're not always going to be the same. And when they're not the same, we need to get them to be the same. We need to get them to match. We need to get them to have the same denominator. Because once we get the denominators back to being the same, then we can add or subtract. Because an example of this here would be, say, 2/5 plus 3/6. As much as we would like to just add and say that this is 5/11, that is not the case. We just can't add that way. So at this point here, we have to find the first number that we can turn both 5 and 6 into. And there's different ways to go about that. We're going to do that here in a minute. But it actually works out that the first number is 30. So for our 2/5, we're going to have to multiply it by 6 over 6. Our 6 times 2 is 12. Our 6 times 5 is 30. On the other side, 6 times 5 is 30 on bottom. 5 times 3 is 15. 27 over 30, which actually reduces to 9/10. So, yeah. But again, it's getting those denominators to be the same, because once we can get there, it's going to make things nicer. Now, realistically, 2/3 plus 3/6, we could stick that in a calculator. It would do it for us. There's not a whole lot of issue there. But with our rational expressions and rational equations, we're going to have variables coming into play. All the calculators that we have don't like using variables as a variable. They need a number. So the first thing we're going to look at is least common multiple. Least common multiple is the first number we can turn, in this case, 8, 14, and 16 into. What is the first number that we can get there? Now, there's two main ways to do this. One of them is skip counting. And what that means is we're going to start off with 8. It's listing every multiple of 8. So 8, 16, 24, 32, 40, 48, 56, 64, 72, 80, 88, 96, 104, 112, 120. And it keeps going on, because again, multiples of 8 go out indefinitely. So it's almost, let's put enough out there just to make sure we have enough. We do the same thing with 14, 28, 42, 56, 70, 84, 98, 112, 126. Oh. That is kind of nice that 112 worked. Yep. And that's the only one between 8 and 14 that did work, is 112. Now we can do the same thing with 16. And hopefully 112 works, because if it does, it's going to be our least common multiple. If not, we're going to have to keep going out farther. Oh yeah, 56 does work. I missed that one. So 56 or 112. So let's see 56. Hopefully 56 will work. 16, 32, 48, 64. Well, we just skipped past 56, so it's not going to be it. 80, 96, 112. Questions on how we found this here? Got any questions, Tristan? Now, yes, this works. This will work every single time. But if that least common multiple starts getting to be bigger and bigger numbers, this is going to take longer and longer to do. So there is another method. And the other method is going to be revolving around factors, the prime factorization of these numbers. We're going to go back to, I think, probably middle school. We're going to do factor trees. We're going to factor tree each one of these to the prime factorizations. And we always start with our small prime numbers. We're not going to use 1 because, well, 1 is not a prime number. So 2. Well, 2 is to a factor of 8. Well, yes, it'd be 2 times 4. Well, 2 is a factor of 4, which is 2 times 2. So that is simplified as it gets, because 2, 2, and 2 are our prime factors. And we have how many 2's? 3. So we can say that 8 is the same as 2 to the third power. Let's look at 14. Well, 2 works. It would be 2 times 7. It's 7 prime. Yeah. So the factorization for 14 is just 2 times 7. 16. We have what? 2 times 8. Well, 8 is 2 times 4, and 4 is 2 times 2. So the prime factorization for 16, we have 2 times 2 times 2 times 2, or 2 to the 4th power. Yes. Now the least common multiple from this here, we want whichever one of these has the most factors of a given factor. So let's look at 2 first. Okay? So out of all the 2's, for 8, how many 2's do we have as a factor? 3. Okay? For 14, how many 2's do we have? 1. And for 16, how many 2's do we have? 4. So we look at all of them with their factors of 2, and whichever one has the most, that's how many 2's we take. So 16 had the most at 2 to the 4th. So for our least common multiple, I know I'm going to need 4 2's. Because again, we're trying to get them to be the same. And the least common multiple is always going to be equal to or bigger than the biggest number. Because again, we're trying to make them all be the same. We're wanting to go up, not down. So that covers the 2's. Well, the only other factor is 7, yes? 14 has 1. How many factors of 7 does 8 have? 0. How many factors of 7 does 16 have? So we need 7 one time.
Holy moly.
And at this point, we can plug it in to a calculator. We can tell it just what is 2 to the 4th times 7 is 112. So this does give us the least common multiple, especially with our numbers, and it gets us a lot faster than having to go and list out every single one. And again, the least common multiple, we're looking for the first number we can turn all 3 of these into. So we know if I'm going to get this here, get 8, 14, and 16 to be the same, I know that the number of each factor needs to be the same. So with 8, it does have 3 2's. For it to match up with 16, I need 4. So that means I can multiply this 2 to the 3rd by another 2 to give us 2 to the 4th. The 14 has 1, but how many more do I need? I need 3 more. Now it is 4. That's why we take whichever one has the most, not how many we have total. So that when we get them there, because I can add 3 more 2's, or I can add 2 more 2's, we can get it to 4. The last 16 does have 2 to the 4th, but it's missing the 7. The middle one already has the 7, and 8 is missing the 7. So it does give us, the least common multiple tells us what the first number or expression would be, and it also gives us an idea of what we need to do to the 3 terms to get them to be the same. Questions on this here? This here is normally where, or one of the more challenging parts of this, is getting these to be the same and seeing what's going to make them be the same. Questions on this here? Okay. We want to find the least common multiple between 9, 12, and 15. I'm going to do the skip counting method here. If you want to, you can. I don't know if I would want to write these down, but because for 9, 18, 27, 36, 45, 54, 63, 72, 81, 90, 99, 108, 117, 126, 135, 144, 153, 160, 171, 180, 189, 198. I'll stop there. 12, 12, 24, 36, 48, 60. We did have 36 match up. 72, 94, 106, 118.
Correct me if I'm wrong, but the fact that 15 against 5 means that it has to be something that has to be under the interval 0 or 5, right?
Yes. So that means 36 and 72
Automatically not it.
aren't going to work because with 15 it has to end in a 5 or a 0. 145.
90. Well,
90 would work with 9 and 15, but 12 blew past 90.
shut up, Ray. The teacher already told me off.
Oh, we got off.
What was the food?
I was like, wait, that's, it was 130, we're going by 12s, 142, 154, 166, make sure I didn't get off, 8, yep, 12, 24, 36, 48, 60, 72, 84. All right, guys. '84, '96, 108, 120, 132, 144, 156, 168. Looking like 180 is probably going to be it. 15, 30, 45, 60, 75, 90, 105, 120, 135, 150, 165. Yep. So this one here, we had to go all the way out to 180. So, Ray, guys, focus up here. So this here, skip counting, I don't think is effective. It will get there. It will get the job done, but it's going to take a lot longer than if we look at the factors of 9, 12, and 15. Well, 9 is 3 times 3. 3 squared. 12, we can start with 2, and 2 times 6. 6 would be 2 times 3. So 2 times 2 would be 2 squared. Times our 3 would give us 12. 15, 2 is not a factor, but we do have 3 and 5. All right, guys. So when we look through these here, we can start with 2. Well, the only number in our group of 3 here that has factors of 2 is our 12, and we have 2 of them. So 2 squared would be part of the least common multiple. Now we can look at 3. Now 15, 12, and 9 do all have 3 as a factor. Which one of these has the most? 9, and it has 2. So for our least common multiple, we'll need 2 3s. And the last factor we have is what? 5. Only shows up once, so we'll need it once. All right, guys. Ray, guys. Ray, JB, up here. Focus. Let's see what 2 squared times 3 squared times 5 is. So again, whichever way you find easier, find that you understand better, do it. Do it, because both of them will get you to the same answer.
Look it up, put it in.
And we'll get that there.
I can't read it.
144. We'll stop there. We're going to finish this up tomorrow.
Sweet.